Welcome to Unit 2. So this is a short unit with just 2 lessons, and each of them are examples of how the basic rules of algebra from Unit 1 are used, in one case in statistics, and another case in political science, used in ways that you might encounter in your first quarter here in grad school. So this unit is kind of a chance for you to check your familiarity with those Unit 1 topics. If you feel like you're not following the logic here, that's a sign to go back and look at or relook at the Unit 1 videos. What you're going to see is this sort of basic algebra of real numbers. The things that you did in Unit 1 underlies everything else we do in math camp, everything we do in the method sequence, everything that you're going to need to become a technically proficient social scientist. Okay. So this first lesson is an example from statistics. And what we're going to do is we're going to talk about a couple of terms that I'm guessing many of you have encountered before. If you haven't, no big deal. You're going to encounter them again. We're going to spend a lot of time in 200A talking about random variables and talking about expected value. And in 200A, we're going to talk about kind of the big picture of what they mean. Here, I'm more interested in your ability to follow the little picture. Okay, so I'm more interested in whether you can follow the argument that I'm going to make that's going to start from a definition of a particular random variable, defining what we mean by expected value, and then answering a question that looks kind of like an algebra question here. A question about whether we get the same answer if we square a random variable first and then take its expected value, or if we take the expected value first and then we square it. Okay, so that's where we're going here. A preliminary thing that I want to say is I can't recommend strongly enough that while you're watching these videos, you're taking notes with pencil and paper. It's so easy to zone out through these algebraic arguments and just be sort of nodding along. Yeah, sure, yeah, sure, yeah, sure. It's easy enough to do that even when you are taking notes, but it really, really will help you if you are writing out your notes in longhand on paper. If it's messy, like your writing is messy, you might notice that I am in that category too, although I'm doing my best to not be messy in these videos. If it's messy, so much the better, because that means you go back and you either recopy it by longhand neatly, or you type it in or something like that. Every time you go through it, you're making that process your own, and it's just critical to how people learn fluency in algebra. Okay, so with that, let's get going. Let's talk about random variables. So a random variable is what we use to represent something we're uncertain about, something that we don't know for sure. Maybe it's random. It seems random to us just because we don't know it, and other people do, or maybe it is truly random. It's just something that isn't completely determined. A random variable in this context is also an example of a mathematical object that's bigger and more complicated than a single number. So in Unit 1, we talked about the algebra of real numbers, and they're kind of the simple building blocks that all of our more complicated mathematical ideas are built on here. So a random variable is one of these more complicated objects. And what we're going to see over and over again is, as we understand what we can do with random variables or matrices or functions or any of these other bigger, more complicated mathematical things, all of the rules for these more complicated things derive from the rules for the algebra of real numbers. All the more complicated mathematical objects are based on real numbers, and the rules for manipulating them come from the rules of real numbers. So you're going to see an example exactly that in this lesson. Okay, so let's first think about a random variable. Let's call it x. I am going to, that's supposed to be a big uppercase. x, and I'm going to use that to denote the random variable. I'm going to try and write lowercase curlier letters to denote the numbers that make it up. Okay, so let's think about random variable x that can take value x1 with probability p1, or value x2 with probability p2. Okay, so that's an example of a random variable. Or we might think of another random variable. Let's call it y. Y. It's maybe a more general case. Here, it takes value x1 with probability p1, value x2 with probability p2, x3. You get the picture here. How many values does it take? Oh, I don't know. Let's just call it n. Take any number of values you want. Probability x value xn is pn. Okay, so these are both valid random variables as long as one thing is true in both cases. Okay, so for x, we need to have, didn't need to do that, p1 plus p2 need to sum to 1. Okay, that's the thing about probabilities. The probabilities always have to sum to 1, and we'll get another thing we'll talk about more in 200A. For random variable y to be a valid random variable for us to work with, we need to have the sum as I goes from 1 to n of all pi's that's y there. Okay. So in both cases, we've got this rule that the probabilities have to sum to 1. So good. I've just defined 2 random variables for us. What do I do when I take their expected value? Okay, so expected value is something that we use when we have something that's uncertain and we want to compare it to something certain. That's one context in which we use expected value. We use expected value actually in all sorts of contexts, but that's maybe one of the most concrete ways to think about it. If we were going to take the bet implied by random variable x over and over again, how much would we expect to win on average over the long run? We'd answer that question by calculating the expected value of x, which is p1 times x1 plus p2 times x2. Okay, so just note what I'm doing here. I've just defined the expected value for a random variable that takes 2 possible values here, and for y that takes a bunch of values. Expected value of y is the sum as I goes from 1 to n of pi xi. I just noticed that I defined the realizations of y using x's again. I could make them y's. It doesn't really matter what variable I use. They can just be as long as it's a number. Okay. So here's the definition in the context of a random variable that takes n realizations. So from a mathematical point of view, the fact that we call one x and one y doesn't matter at all, but it's kind of relevant that that x takes 2 possible values and y takes just y takes n, an arbitrary number. Okay, so that's a thing I can do. Expectation is an operation I can perform on a random variable. Notice I can't take the expectation of just a number, because if I take the expectation of a number, well, I've got to have probabilities and outcomes to calculate it. I have to have something that I can decompose into the x's and the p's here. Second thing to notice is, so taking the expected value is something I do to a random variable. When I do it, what I get is a real number, right? The answer is a number. So another way to think of expected value is you've got all this complicated information in the random variable. Can you come up with one number to summarize it? Yes, you can. And if you're going to have just one, the one you would pick would be the expected value. Every component of the random variable x1, x2, p1, p2, they all are here in the expected value. Okay, expected value is great. So what we want to do now is we want to come up with what you might think of as an algebraic rule for expected value. That's the title of the lesson, the algebra of expectations. And you'll remember from the algebra of real numbers, a lot of those rules have to do with, can we switch the order of operations? Can we add things first and then multiply? When can we do that? Sometimes we can. A lot of the times we can with numbers. We can't always. We can't do it when we're raising to powers, for example. But though the answer to those questions are algebraic rules. So we're going to look at a potential rule for expected value, a rule about the algebra of expected value and really about the algebra of random variables. But we're going to figure out whether it holds or not based on the algebra of real numbers. So let's just go ahead and do that. And okay. So I'm going to do it in the context of the simpler random variable, the one that just takes two values here. So RV RV in this world stands for random variable, takes value x1 with probability p1, x2 with probability p2, just copying over everything. So the expected value of x, uppercase big letter here because it's the random variable, is x1 p1 plus x2 p2. Of course, I can write that in any order I want here. Another thing I can do to that random variable is I can square it. And so when you square or you perform any function on a random variable, what that means is you perform the function on the outcomes and you leave the probabilities the same. Okay? So if the random variable is a bet where I get $10 with probability 0.4 and 0 with probability 0.6, and then I want to think about what's another random variable that would give me the square of that. That would be a random variable that would give me 100 with probability 0.4 and 0 with probability 6. Okay? So just summarizing that, the new variable, x squared, it's sort of new, but it's sort of not. It's a function of the old random variable. So if we know that original random variable x came out to be x1, well, x squared would be x1 squared. And if we knew that original random variable capital X came out to be x2, the new one would be x2 squared. What's the probability that this new random variable takes the value x1 squared? Well, it's the same p1 probability that x took the value x1, and the probability that x took the value x2 is still p2. Okay, so anytime you perform a function on a random variable, you're performing it on the outcomes, leaving the probabilities alone. And notice we can now take the expected value of x squared. It's a new random variable. X squared takes value p1. Takes value x1 squared with probability p1 and value x2 squared with probability p2. All right. So the question we were asking is, does the answer we get if we square the random variable and take its expected value, is that the same as what we get if we take the expected value first and then square it? That was true. That would be nice. That would mean that we could simplify things in ways that we would like. Let me make sure that I'm, that's 2 there. Square of the variable. Well, are they or are they not the same? Well, we're going to answer that in terms of the algebra of real numbers, because everything now, once we've taken the expected value, over here, This is a real number. All of these are numbers. We're multiplying, we're adding up, we're getting another number. These are also numbers. We're multiplying, we're adding them up, we're getting another number here. So we're going to see if we take the expected value of x and we square that number, do we get the same answer as if we square the random variable first and then take its expected value. Okay. So we've already got the expectation of the square of the random variable. That's lovely. Now we need to multiply out the x1p1 plus x2p2 that times itself. Okay. So this number is just an expression for the expected value of x. I'm multiplying it by itself. That's what it's telling me to do here. Take that expected value of x, that number, multiply it by itself. Okay, well, we can do this. This is starting to look like the stuff we were doing in Unit 1, right? So let's multiply the first term by both of these and then the second term by both of those. That's my little system there. Okay, and I think I'm going to switch the order of the p's and x's to match the way I wrote it on the other side. That doesn't really matter. It just makes it a little bit neater here. So multiplying the two first terms together, I'm going to get p1 squared times x1 squared. And multiplying this first term times the second one gives me p1 p2, x1, x2. Okay, so I've multiplied this first term by both of these. Now I need to multiply the second term by both terms in the second factor. Multiplying this guy times that guy gives me another p1, p2, x1, x2. And multiplying the two last terms together, I get p2 squared plus x2 squared. Okay. Well, that's not super pretty. Let's maybe, we combine those two middle terms. It's equal to p1 squared, x1 squared plus 2 p1, p2, x1, x2. Oh yeah, we should recognize that as kind of the formula of a perfect square anyway. P2 squared, x2 squared. Well, it's not obvious that these two are the same at all. In fact, the more we look at them, the more we might think, yeah, they're probably not the same. For one thing, we've got this complicated term that depends on p1, p2, x1, x2 all together in the expression for the expected value of x itself squared. Nothing like that up here, right? We've also got squares of the probabilities in this, and only the non-squared terms here. So it's not looking real promising. These are not obviously. Okay, but you know, that's kind of an impressionistic reaction. This is a math class. We're supposed to be systematic here. So the way I want to look at this is, I'm going to go to a new page for my new way to look at it. We're going to ask ourselves, when does the expected value of x squared minus the expectation of x squared equals 0? If that's true, it means they're equal. So again, this is kind of a solving technique that we saw in Unit 1, and we're just going to substitute for those things. Okay, so for the expected value of x squared, remember that is p1 x1 squared plus p2 x2 squared. So that's the first term, and now we're going to subtract off the expectation of x, that number squared here. So we're subtracting off the more complicated expression that we just derived here. It was p1 squared x1 squared plus 2 p1 p2 x1 x2 plus p2 squared x2 squared. When does that equal 0? Okay. Back to just the rules of basic algebra here. Let's distribute the negative sign here in combined terms. So doing that, I'm going to combine the x1 terms here. And I need to be careful. I've got, sorry, the x1 squared terms. X1 squared times p1 minus p1 squared. And so here's my p1, here's my p1 squared. I'm being careful about that, that negative sign there. Good. And same for the x2 squared term. X2 squared, I've got a p2 here and a negative p2 squared. P2 minus p2 squared. And then the final term, don't have anything really to combine it with here, so we'll just recopy that guy. Again, remembering that we're subtracting off every term in parentheses here, so it gets a negative sign too. So minus 2 p1, p2, x1, x2, and we're still wondering when that equals 0. Okay, so let's do a little more factoring. This is the story arc that we see a lot when we're doing algebra. The expressions, not clear if it's getting simpler or messier, but let's kind of keep going because sometimes they get messier and then we find ways to simplify them, and that's super gratifying when that happens. So I've got my x1 squared here. I'm noticing I can factor out a p1 here, and so I'm going to do that. x1 squared times p1, left with 1 minus p1. And I'm going to do the same thing with x2 squared term times p2 times 1 minus p2. This other term, nothing I can do with it except just bring it along every time. Okay, so now I'm going to use something that we might have forgotten about. Remember, these p's aren't just any old numbers. They have to sum to 1. Okay, so I'm going to use the fact, let's get a different color here, that p1 and p2 have to equal 1. I'm going to observe that this is actually p2 and this is actually p1. How about that, right? Because p1 plus p2 equal 1. They're not probabilities if they don't equal 1. So I'm going to substitute that. So I have x1 squared p1 p2 plus x2 squared times p1 p2 minus 2 p1 p2 x1 x2, that whole thing equals 0. Well, now look at that. Now I have, I write all the subscripts, right? I'm missing a p2 right here. Now I have p1, p2 in every term. I can factor that out. So I'm going to do that. So I get p1 times p2 times x1 squared plus x2 squared minus 2 x2, that whole thing equals 0. Now we're getting somewhere. Oh, and look at this. Look what I've got in parentheses here. It's written in a different order than we otherwise would, but this is the formula for x1 minus x2 squared. Remember that x1 minus x2 squared equals x1 squared minus 2 x1 x2 plus x2 squared. So I can substitute that too. Now I'm getting to something that looks, generally does look simple. P1 times P2 times x1 minus x2 squared equals 0. Okay, that's something we can talk about. Now let's think about what that means. Okay? We started off this whole chain of algebra asking ourselves, when does the expectation of the squared random variable equal the square of the expected value? And we wanted to know that. And the reason why we wanted to know that is when that's true, it means that we can switch the order of doing those two things. Now we know, okay, this tells us the conditions under which we can switch the order of squaring and taking the expected value. And those conditions are, there's three possibilities, okay? Three possible ways to make this true. This is, I'm not sure we need that this is a special enough thing. Let's switch to purple for that. So this is true if P1 equals 0, okay? P1 equals 0, that whole thing equals 0 because we're multiplying something by 0. It's also true if P2 equals 0, so either one, or if x1 equals x2. Okay. Those are the conditions under which we can switch the order of squaring and taking expectation. Well, okay, good. That's good to know. Let's think about what this means, though. If one or the other probabilities equals 0, it means there's really no uncertainty. If P1 equals 0, what that means is that P2 equals 1. Okay. Or if P2 equals 0, it means P1 equals 1. There's no uncertainty. We don't need a random variable. This is way too much complication that, that doesn't get us anywhere. Or if x1 equals x2, again, it doesn't matter. Okay, so this is true only if there is no randomness. And not to give away something we'll do in 200A or something that many of you have seen before, if this is true, the random variable is going to have 0 variance. Okay, that's another way of thinking of something that we might think is uncertain, but it's really not. All right, so that's kind of getting into the big picture. The lesson here for today, and the important thing to remember in general, you cannot switch the order of squaring first and then taking expected value, or taking expected value. Okay. And this is also a pattern that we're going to see over and over again. Numbers are actually pretty forgiving. The algebra of real numbers gives us a lot of possibilities for switching the order of operations as we move up through taking derivatives and multiplying matrices and things like that. We're going to find more and more things that we have to do in a certain order, that we can't switch the order, that the algebra isn't as fluid as it is for real numbers. Okay, so as I say, the important thing for this video is, can you follow basically this part of the argument? If you can, that's great. If you're feeling a little bit nervous about parts of it, go back through lesson 1A, helps you on the basic solving thing. That we did some factoring here as well. That might be another lesson to look at. You've got a quiz problem that's got numbers in it that's going to help you check this logic. And then we've got a workshop that's going to use a similar logical process to look at a different question about the algebra of random variables. So have fun with that stuff.